Welcome back to The Deep Dive. Today, we're doing something a bit different, kind of a historical reconnaissance mission.
Sounds intriguing.
We're stepping back, trying to get into the scientific mindset of 1922. We've got this expert summary of atomic theory, published right on the cusp. I mean, just before quantum physics blew everything wide open.
Ah, yes. That's a fantastic snapshot in time. It really is. Because when you read things from that exact moment, you see this incredible progress they'd made in the 25 years leading up to it?
Right.
They'd finally managed to sort of stitch together the chemical view of the atom, which was all about how things combine, weights and ratios.
Yeah, the practical stuff.
With the physical view, which was motion, speed, electricity. These were almost different worlds for a long time.
So a grand unification just before the next revolution.
Pretty much.
And here's the goal for you, listening in. We want you to really feel the struggle they faced, like this basic confusion between atomic weight and, equivalent weight?
Exactly, and how clues just sort of popped up unexpectedly.
Like radioactivity, that glowing radium.
Or even just, specks of dust jiggling in water, things that forced them towards a model of matter that,
That should have just collapsed instantly, based on everything they knew.
that's the crisis we're heading towards. It's quite a story.
Okay, let's dive in. Where does the chemical story really kick off?
Well, you really have to start with John Dalton. The key thing about Dalton is he didn't just use atomic theory to explain stuff they already knew. No, he used it as a guide. Like, if atoms are real, then this is what we should find.
So predictive, not just descriptive. What were the rules?
3 big ones, confirmed by experiment. First, constant proportions. Simple idea, profound impact. Elements always combine in the same weight ratios. Water is always the same ratio of hydrogen to oxygen by weight. Doesn't matter how you make it, where you find it. Fixed.
Okay, straightforward enough.
Second, multiple proportions. This is maybe the strongest hint that you're dealing with discrete units, with atoms. If 2 elements, say nitrogen and oxygen, can make different compounds.
Like nitrous oxide and nitrogen dioxide.
Exactly. Then the weights of oxygen that combine with a fixed weight of nitrogen will be in simple whole number ratios. Like 7 parts nitrogen might combine with 4 parts oxygen in one case, and 7 parts nitrogen with 8 parts oxygen in another.
That 4 to 8, a 1 to 2 ratio, it screams building blocks.
It really does.
Yeah.
And the third was continuous proportions, basically linking how different elements combine with a common third element.
Okay, so these laws gave chemists a framework, but you mentioned a problem, the weight conundrum.
Oh, it was a mess.
Right.
A real conceptual roadblock for decades. They couldn't easily figure out the true atomic weight versus the equivalent weight. The equivalent weight is just what you measure directly in an experiment.
How so? Give me that water example again.
Right, water. And analysis shows you've got 8 times more oxygen than hydrogen by weight. Okay, fine.
Right.
But what's the formula? If you assume it's simple, 1 atom of each, HO, then oxygen's atomic weight must be 8 relative to hydrogen being 1.
Makes sense.
But if you assume the formula is actually HO, 2 hydrogens for every oxygen.
Then that same experimental weight ratio means oxygen's atomic weight has to be 16. Double what you thought before.
Precisely. You get totally different fundamental weights depending on the structure you assume, and they couldn't see the structure.
It's like trying to weigh bricks, but not knowing if you've got 1 brick or 2 stacked together.
That's a perfect analogy.
Right.
Total confusion.
So who cracked it?
It was Avogadro. But sadly, his work was mostly ignored for about 50 years. He built on Gay-Lussac's work. Gay-Lussac noticed gases combine in simple volume ratios, like 2 volumes of hydrogen gas plus 1 volume of oxygen gas gives you 2 volumes of water vapor. Simple numbers again.
Okay, volumes now, not weights.
Yes. And Avogadro had the brilliant insight. Equal volumes of any gases, if they're the same temperature and pressure, contain the same number of molecules.
Molecules, not atoms. That's the key distinction.
That's the absolute key. He realized you had to distinguish the fundamental particle of an element, the atom, from the smallest particle of a substance that can exist freely, the molecule. So hydrogen gas isn't just H, it's H-euro. Oxygen gas is O, if you think of it that way.
Then the 2 volumes of H plus 1 volume of Oro making 2 volumes of H-euro makes perfect sense, and the 1.16 weight ratio works out.
Exactly. It took a while to sink in, but distinguishing atom from molecule solved the weight problem.
Okay, so weight's sorted. Now chemists can actually start thinking about structure, right? That's where organic chemistry comes in.
Yes, precisely. Concepts like valence became crucial, or Wertigkeit, as the Germans called it. Basically, an atom's combining power. How many hands does it have to link up with others?
And this let them draw molecules.
Absolutely. Think about carbon. It's tetravalent 4 hands. That immediately suggests it can link to four other things, or link to other carbons to form chains and rings. It unlocks structural chemistry.
Like Kekulé figuring out the benzene ring structure.
The classic example. That closed ring of 6 carbons. A huge triumph. So by, the early 20th century, the chemical atom was pretty well understood structurally.
Okay, so the chemists mapped out the rules of combination, the structures, but the physicists were asking different questions, weren't they? Like, are these things even real, and what are they doing?
Right. The physicists brought in motion. The big shift was accepting the kinetic theory of heat. Heat wasn't some weird invisible fluid as people used to think. It was the motion, the kinetic energy of these tiny particles, atoms and molecules. Clausius, Maxwell, they really established this.
And this wasn't just a nice idea, it actually made predictions.
Oh, yeah. It was powerful. First, kinetic theory could mathematically derive all the known gas laws, Boyle's law, Charles's law, just in the mechanics of particles bouncing around.
Okay, connects to known physics.
Second, it independently confirmed Avogadro's hypothesis about equal volumes having equal numbers of molecules. It fell right out of the math. The chemical molecule and the physical molecule were the same thing.
Nice convergent.
And third, maybe the coolest prediction was about specific heats, how much energy it takes to heat up a gas. The theory predicted that monatomic gases like argon or helium, where the atoms are just single points whizzing around, should have a slightly different specific heat ratio than polyatomic gases, like water vapor or geoair, where the molecules can also rotate and vibrate.
Because some energy goes into that spinning.
Exactly. And the measured values matched the predictions perfectly. It was incredibly strong evidence for the physical reality of molecules.
Wow. Okay, and the speeds involved. You mentioned the source talks about hydrogen molecules.
Yeah, it's kind of mind-boggling, about 2 kilometers per second.
That's faster than a rifle bullet back then.
Way faster. But the catch is, they don't get far. The air is so crowded, they're smashing into other molecules hundreds of millions, maybe billions of times every second.
So constant chaos. Which leads to the next big question, I guess. How many of them are there?
The ultimate question for atomism back then. What is the actual number of molecules in a standard amount, in a mole? That's the Loschmidt number, usually called Avogadro's number today, capital N.
And they had a value by 1922.
They did. The source we're looking at cites $60 6 times 1022. That's 606 sextillion, an almost unimaginable number.
How could they even measure that? It seems impossible.
Several different ways, amazingly. Gas viscosity, diffusion rates. But maybe the most convincing evidence came from something totally unexpected.
Which was?
Brownian motion. Remember Robert Brown, the botanist, back in 1827? He saw pollen grains suspended in water jiggling around randomly under his microscope.
Yeah, I remember that. Always seemed a bit weird. Why would they move?
Well, for decades, nobody knew.
Hmm.
Then Einstein, in 1905, provided the explanation. It's the water molecules, invisible but constantly moving, bombarding these larger visible particles from all sides.
Ah, so the jiggling is just the particle getting knocked around unevenly.
Precisely. And here's the genius part. Scientists like Perrin and Svedwin realized you could treat these visible jiggling particles as sort of giant molecules. By carefully measuring how much they moved, how fast they diffused, you could actually work backwards using Einstein's equations to figure out the underlying molecular bombardment rate,
And that let them calculate.
the mass of the individual water molecules, and from that, independently calculate the Loschmidt number again.
And it matched the number they got from gas physics.
It matched remarkably well. Seeing that visible jiggling confirmed this invisible number. Well, it pretty much settled the debate. Atoms and molecules were real.
Okay, so the atom is real, structured, numerous, and constantly in motion. Things are looking pretty solid. But you said this is where things start to break down.
Yeah, the ground starts to shake, you could say. And electricity is the trigger. Michael Faraday's work on electrolysis back in the 1830s was the first clue. He showed that when you pass electricity through chemical solutions, the amount of substance deposited is directly related to the amount of electricity used. And crucially, the same amount of electricity was needed to deposit one equivalent weight of any substance. It strongly suggested electricity itself wasn't continuous, but came in packets, units, and atomism of electricity,
Leading to?
the electron. Experiments with cathode rays those beings in vacuum tubes showed there were streams of particles, negatively charged particles, moving very fast.
And they measured their properties.
They did. J.J. Thomson and others deflected them with electric and magnetic fields. And the shocking result was the mass. These electron particles were incredibly light, only about 11/100th the mass of a hydrogen atom, the lightest known atom.
Whoa, so parts inside the atom.
Exactly. That discovery around 1897 was really the point of no return. The atom wasn't the fundamental, indivisible thing Dalton imagined. It was a composite. It had an internal structure.
Okay, the atom has pieces, but then comes something even more dramatic, right? Radioactivity.
Right. Becquerel's accidental discovery with uranium salts, then the Curie's isolating radium. This stuff glowed. It emitted energy continuously, intensely.
And the energy source was a total mystery.
Complete mystery. It didn't seem to follow any chemical rules. Heating it, cooling it, reacting it didn't matter. Radium just kept pouring out energy, seemingly from nowhere.
What was the explanation?
It took the boldness of Rutherford and Soddy around 1902, 1903. Their theory was radical.
Yeah.
Spontaneous atomic decay. The atoms weren't stable. They were spontaneously disintegrating, transforming into other elements, transmutation, the alchemist's dream, but happening naturally.
The atoms were literally falling apart and releasing energy as they did.
Yes. And they identified the emissions, the rays, 3 types.
Okay, what were they?
Beta rays turned out to be just fast-moving electrons, same as the cathode rays. Easy enough. Okay. Gamma rays were high-energy light, like super powerful X-rays, electromagnetic radiation.
Got it.
But the alpha rays were the really interesting ones. They were heavier particles, positively charged, and didn't penetrate very far, but hit hard.
And what were they?
Rutherford suspected, and Ramsay later proved spectroscopically, they were helium atoms, but stripped of their electrons. So positively charged helium nuclei.
So the atom isn't just made of electrons, it's throwing off chunks of its core, chunks that are other atoms.
Essentially, yes. And this led to the crucial decay rule figured out by Fagans and Soddy. When an atom spits out an alpha particle, helium nucleus charge +2, it transforms to an element 2 steps back, left, in the periodic table.
Okay.
When it spits out a beta particle, electron, charge magical 1, it effectively turns a neutron into a proton in the nucleus, so it transforms to an element 1 step forward, right in the periodic table.
Wait, so the element's identity, its chemical nature, changes based on these decays, which means it can't just be about the weight anymore. Weight changes, sure, but the position in the table shifts in this very specific way.
You've hit the nail on the head. That was the huge realization. Chemical identity isn't fundamentally determined by atomic weight.
Because that also explains those weird inversions in the periodic table, right? Like tellurium and iodine. Tellurium weighs more, but comes before iodine chemically.
Exactly. Weight wasn't the defining property.
Sure.
The defining property, proposed by Vandenbroek and championed by Moseley, was the atomic number. A whole number representing the positive electrical charge on the nucleus. That's what dictates the number of electrons, and therefore the chemistry.
So charge, not weight. That's the key.
That's the fundamental shift. And it immediately led to the concept of isotopes. Elements that have the same atomic number, the same nuclear charge, same number of electrons, same chemistry, but different numbers of neutrons in the nucleus, so different atomic masses.
Ah, like different versions of the same element.
Precisely.
Okay.
Our 1922 source mentions lead having, I think, 6 known radioactive isotopes, plus the stable one we know. Same chemistry, different weights.
And Aston's mass spectrometer confirmed this for regular elements, too.
Yes, Aston's work was definitive. He showed elements like chlorine, neon, krypton, xenon weren't pure weights. They were mixtures of isotopes, each having very nearly whole number masses relative to hydrogen.
So, in a way, it brought back Prout's old idea from 1815, that everything is built from hydrogen.
It revived it in a modern form. The fundamental building blocks seemed to have whole number masses, and the non-integer atomic weights we measure were just averages of isotope mixtures. It was a beautiful clarification. Charge dictates identity, isotopes explain the masses.
Okay, so the chemical identity is now clear. Based on atomic number, we know atoms decay, we know they have electrons. What about the overall picture, the structure?
That came largely from Rutherford again, using those alpha particles as probes. His team fired them at thin gold foil.
The famous scattering experiment.
The very one. Most alphas went straight through, maybe slightly deflected, but a tiny fraction, maybe 1 in 8,000, bounced back dramatically.
Like firing a cannonball at tissue paper and having it bounce back at you, as Rutherford said.
Exactly. It was shocking. It meant the atom wasn't like a pudding with electrons scattered through it, as Thomson had thought. It had to be mostly empty space, allowing most alphas through. But with something incredibly small, dense, and positively charged at the center, capable of deflecting an alpha particle right back.
The nucleus.
The nucleus. The calculations showed it must be unbelievably tiny, maybe 10, 13 centimeters across, compared to the whole atom being 10 centimeters. Almost all the mass concentrated in this minuscule point.
So that leads directly to the model they had in 1922.
The planetary model. A tiny, heavy, positive nucleus, the sun, with light, negative electrons, the planets orbiting it. The number of electrons matched the positive charge, the atomic number, to keep the atom electrically neutral.
It fits the evidence, the
Yeah.
scattering, the electron, the neutrality.
It seems necessary, right? It accounts for everything they discovered.
And here comes the crisis we talked about. This model had fatal flaws, didn't it?
Two absolutely catastrophic ones, according to classical physics, flaws that were staring them right in the face in 1922.
What was the first one?
Spectra. The model implies electrons could orbit at any distance from the nucleus, like planets can. If that were true, atoms should absorb and emit light at all frequencies, producing a continuous spectrum, like a rainbow.
But they don't.
Not at all. What we actually see are incredibly sharp, distinct lines, specific frequencies, unique to each element, like a fingerprint. Think of the thousands of sharp lines in the spectrum of iron.
How could the planetary model explain that? Why only certain orbits, certain energies?
It couldn't. There was absolutely no reason within the model for electrons to prefer specific orbits. That was flaw number one.
Okay, bad enough. What was the second flaw?
Even worse.
Yeah.
Total instability. According to the bedrock laws of classical electricity and magnetism, Maxwell's equations, an accelerating electric charge must radiate energy. It's not optional. It's fundamental.
And an electron orbiting a nucleus is accelerating, right? It's constantly changing direction.
Constantly. Which means it must be constantly radiating away its energy as light.
And if it loses energy?
It loses speed. It can't maintain its orbit. It should spiral inevitably, inexorably, into the positive nucleus.
How quickly?
Calculations showed it should happen almost instantly. In a tiny fraction of a second, the atom should collapse.
So the model demanded by all the experimental evidence, radioactivity, scattering, the electron, was a model that classical physics said couldn't possibly exist for more than an instant.
That's the perfect crisis of 1922. A necessary structure that was fundamentally, theoretically impossible according to the physics they knew and trusted.
Wow. Okay, let's try and wrap our heads around this. We've gone from simple weight ratios to discovering subatomic particles, radioactivity, isotopes, landing on a planetary model that seems right but is doomed by the physics of the day.
It's quite a journey. And I think the single biggest conceptual leap in that whole period, the thing that really unlocked chemistry, was shifting the definition of an element away from its weight.
Which was ambiguous because of isotopes.
Exactly. To its fundamental electrical charge, the atomic number, that integer. That clarified everything on the chemical side.
But left the physical atom completely broken according to classical rules.
Utterly broken.
So here's the final thought to leave you with. If the established laws of physics themselves were the problem, if they dictated that Rutherford's atom had to self-destruct, what kind of radical new thinking, what kind of departure from common sense did it take?
What did people like Max Planck, and especially Niels Bohr, have to invent? What strange new rules did they have to impose on the electron to just allow it to stay in orbit without radiating?
That required building a whole new thought world, didn't it? One where the old rules just didn't apply at the atomic scale?
It certainly did. And that, of course, is the threshold of quantum mechanics. A story for another time.